In this video we're going to simplify this square root expression. We have the square root of 720 x to the 7th over y to the 7th. So we have quite a few things to deal with here. We can almost think about separating this into a couple smaller problems and let's just go off to the side and think about how we would deal with the square root of 720. And then we'll think about how we would deal with the square root of x to the 7th and y to the 7th. And the reason we're doing that is there's some rules for dealing with square roots. I'll write them over here, or any roots actually. If you have the square root of a times b, that's the same as the square root of a times the square root of b. You can split it up. If you have the square root of a over b, that's the same as the square root of a over the square root of b, or any root. It could be the cube root. You could put little n's here for the nth root. So we really can look at these as three separate problems, and then we'll put it all together at the end. We do need to remember that the y to the 7th is going to be in the denominator, and we'll have to deal with that as well. Alright, so when we're dealing with the square root of 720 and we want to simplify that, we need to find a perfect square that goes into 720. Our perfect squares are 1 squared, which is 1, 2 squared, which is 4, 3 squared, 4 squared, 5 squared, and so on. So let's just make a list. And I know there's other ways to do this, but this is the method I prefer. Did I miss one? 6 squared, 7 squared, 8 squared, 9 squared, 10 squared, and we could go on. Do any of these green numbers go into 720? Well, some of you may see it right away, some of you are not sure, so you could go off to the side and start breaking down 720. I'll erase this in a minute. This is the method that some people would use from the beginning, and just break it down to its prime factorization. And there's some merit to that, so why don't we show both those ways. See right here I'm seeing 360. I know 36 goes into 360, so I would break up my 720 right now with 36 times, I guess it would be 20, huh? So let's do it that way first, and then we'll come back and finish this prime factorization, because I do think that might be a way that some of you might like to do, or might prefer. Okay, so I just figured out that 36 times 20 is 720. So I'm going to split this up into 36 times 20, because I can take the square root of 36, which is just 6. That's my whole goal, is to try to sort of get stuff out from under this square root. So now I have 20 left under the square root. Do any of these green numbers go into 20? Well, 4 goes into 20. 20 is 4 times 5. So I take the square root of 4, and you could break it apart like I did up here on this step, or you could just think that you're going to take the square root of 4 to get that 4 out. The 6 will come down. When you take the square root of 4, that's going to be 2. And then the 5 is still left in there. So where'd the 4 go? It became a 2 because you took the square root of it. And then it'll multiply on the outside with the 6, and you'll have 12 square roots of 5. So I'm going to write that up here because I'm probably going to end up erasing this. 720 simplifies to 12 square root 5. Let me show you that other way now to get to 12 square root 5 using prime factorization. Okay, so if you're doing a prime factorization, then you usually just keep breaking down by 2's until you can't anymore. So that's my printer. 360 is 2 times 180. 180 is 2 times 90. 90 is 2 times 45. I have to go up here now. 45 is, now 2 doesn't go into 45, so I'll go to 3's. 45 is 3 times 15, and 15 is 3 times 5. So I have 2 times 2 times 2 times 2, 2 to the 4th, times 3 times 3, which is 3 squared, times 5. Okay, so if you're using the prime factorization to do the square root, then what you want to do, I'm going to have to erase this. So if you need to pause the video and write down how we got that prime factorization, go ahead and do that, because I did it kind of fast. Okay. So if you're going to use this, then what you want to do is you want to take the square root of 720, right? So you want to do the square root of all this. When you have an exponent and you're taking the square root of it, you divide that exponent by 2. So the square root of 2 to the 4th is 2 to the 2nd. You just divide the exponent by 2. And the square root of 3 squared is just 3 to the 1st. And if you think about that, 3 squared is actually 9. 3 squared is 9, so the square root of that is 3. 2 to the 4th is 16, so the square root of that is 4. This is kind of why I prefer this other method, because I think the numbers get lost a little bit on people. They just see a bunch of exponents, but either way will work. The 5 has to stay inside there. He doesn't have an exponent that I can divide in half. So then I would multiply this out, and 2 squared is 4 times 3 is 12. So I end up with 12 square root of 5, which is the same thing I got that way. So those are the two different methods for breaking apart a big number under a square root, is to do the prime factorization and then take the square root of those different terms, or focus on these green numbers and break down your big number into one of these green numbers times whatever. And then that green number, you're going to be able to take the square root of it. Those are your perfect squares, these green numbers. Perfect squares. Those you really should have memorized when you're dealing with square roots. They should be something that's easy for you to think of. Then I get to the 20. Is there any green perfect squares that go into 20? Yes, 4. Times whatever. This other number doesn't have to be a perfect square. You just need one of them to be a perfect square. Like up here I had 36 times 20. 36 is a perfect square, 20 is not. That's fine. I just need one. Then I can get that guy out, take the square root of it, and then worry about breaking down the 20 if I have to later. So the 4 was a perfect square. The square root of that is 2. Now I have a 5 left under there, and none of these green numbers go into 5. 5's too small. It's already prime. Nothing goes into 5 anyway. So you're done. Alright, so that's the first part. Let me erase all this. We know how to break down 720. Okay, so now we have to deal with the x to the 7th. Let me start at the beginning with the x's. We know x times x is x squared. Therefore, the square root of x squared would be x. We know x squared times x squared. You'd multiply those exponents together. That gives you x to the 4th. So the square root of x to the 4th takes you back to x squared, because the square root of x to the 4th means what times itself is x to the 4th. That's x squared. All right, let's keep going. X to the 3rd times x to the 3rd, what would that be? X to the 6th, because you add the exponents. So the square root of x to the 6th would be x to the 3rd. What times itself is x to the 6th? X to the 3rd. We just saw it over here. Hopefully you're starting to see the pattern. X to the 4th times x to the 4th is x to the 8th. So the square root of x to the 8th is x to the 4th. If you'll notice, when you take the square root and you're dealing with an exponent, this exponent gets cut in half. I had an x to the 6th, I took the square root, it's x to the 3rd. I had an x to the 8th, I took the square root, it's x to the 4th. And that's how you simplify that. So let's skip ahead, say I had x to the 16th. What's the square root of x to the 16th? Cut the 16 in half and you get x to the 8th. And we could verify that by checking that x to the 8th times x to the 8th is x to the 16th. One little problem I like to give a class when they're first learning these is the square root of 16x to the 16th. The square root of 16x to the 16th, because I want to see that they know that you have to deal with this coefficient of 16 differently than this exponent of 16. The square root of big 16, a coefficient 16, is 4. The square root of x to the 16th is x to the 8th. You have to deal with those differently, so that's an important thing to keep in mind. All right, well, we have x to the 7th. And we have to deal with x to the 7th. Before I erase that, look at this pattern over here of these exponents that we took the square root of. We had x squared, x to the 4th, x to the 6th, x to the 8th, and then it would go x to the 10th, x to the 12th. So you can only take a square root of an exponent that is even because you're dividing it by 2. Well, we've got x to the 7th, so we're going to have to do something about that. So here's what we're going to do. Here's what you do if you have an odd exponent. Finally, we get to cut to the chase here and figure out square root of x to the 7th after all that warm-up. Okay, so we can't take x to the 7th as it is. We need to split it up into an even number. So x to the 6th times x. Basically, you're kind of pulling out one of the x's. X is the same as x to the 1st, so it is true that x to the 6th times x to the 1st is x to the 7th. And why are we splitting that up? It's kind of the same idea as these green perfect squares. If I were to list my green perfect squares for my exponents, it would be x squared, x to the 4th, x to the 6th, x to the 8th, or it could be y, it doesn't matter, x to the 10th, dot, dot, dot. So I need to create one of these green perfect squares over here with my x to the 7th. And you can always do that when you're doing a square root. It's a little different with a cubed root. But with a square root, you just basically subtract 1 and you pull that x off to the side. Still inside the square root. Now I can take the square root of x to the 6th. And that's going to give me x to the 3rd because I'm dividing by 2. Alright, so I lost my color palette. Let's do this. So I have x to the 3rd on the outside, and I still have an x left on the inside. You're going to have a similar situation with your y to the 7th. Okay, so this is x to the 3rd square root x. And similarly, the square root of y to the 7th would be the square root of y to the 6th times y, which is y to the 3rd square root y. Okay, so let's put all this together into one problem and see what it looks like. So on the top, I have the square root of 720, which is 12 square root 5. And then I have the square root of x to the 7th, which is x to the 3rd square root x. And on the bottom, I have y to the 3rd square root y. Now we can simplify the numerator by multiplying the numbers that are outside the square root together, the 12 and the x to the 3rd. So I'll put that out in front, 12 x to the 3rd. And then we can multiply the square root 5 times square root x and just put those together back underneath the square root like that. And then we still have y to the 3rd square root y on the bottom. Alrighty, so now we have to deal with this idea of rationalizing the denominator. It's good etiquette when you're dealing with fractions and radicals to not have any square roots, any radicals of any kind in your denominator. So I'm going to put this in red because we want to get rid of that. We don't like that there. So we have to do something called rationalize the denominator. And I think I have a video on here about rationalizing the denominator. Hopefully, if you're doing a problem like this, you've gotten to the point where you've practiced this with easier problems. But so the idea, it's pretty easy to get rid of this square root y. All we have to do is multiply it by another square root y. Because the square root of y times the square root of y would give us the square root of y squared, which is just y. So it's another property or another rule. Oh, what's that? Let's get rid of that. There we go. It's another property that says the square root of anything squared is just going to give you that number back. So if I multiply the bottom by the square root of y, which is what I want to do to take care of this square root, and you'll see what happens, I have to multiply the top by the square root of y. That's a property of fractions. Whatever you do to the bottom of the fraction, you got to do to the top. This is not an equation thing. We're not doing something to both sides of the equation. We're doing something to top and bottom of a fraction. Essentially, what are we multiplying by here? What is this in blue? It's worth 1. Something divided by itself is 1. So we're multiplying this fraction by a version of 1, which doesn't change the actual value of the fraction. Okay, so let's see what we get here. On the top then, I still have 12x to the 3rd on the outside of the radical. And inside the radical now, let's put a little line here. I've got 5x and a y, so I can put that all together, 5xy. On the bottom, I have a y to the third, and I have a square root of y times the square root of y, which we did over here. Square root of y times square root of y would be the square root of y squared, which is just y. So these two square roots went together to just make a y without a square root. So on the bottom here, I have y to the third times y, which is y to the first. To do that, I add my exponents. So that's going to give me y to the fourth. So I'm going to take a little shortcut here, and I'm going to erase this, and I'm going to write y to the fourth. So again, I got that by taking y to the third times these two went together to make y. And that is pretty much it right there. How do I know I'm done with these things? I mean, it seems like a lot of steps. So here's what you want to check for. Do you have any radicals in your denominator? The answer is no. That's good. That's the first thing you should check for. Second thing, underneath this radical, are there any perfect squares, those green numbers that would go into 5 or x or y? No, I've got that completely simplified. I'm good to go. The other thing you could check for is to see if what's outside the radical would cancel. I have a 12x to the third over y to the fourth. Nothing's going to cancel there. But if I had a 2 on the bottom or something I could cancel with the 12, I would want to do that. But I don't in this problem. So that's how you know you're done, is you check for those three things. There's a lot going on in this video. If it was a little confusing, it might help to watch it one more time or write this original problem down, try it yourself, and then try it yourself without watching the video, without looking at any notes, and see if you can come up with this answer. That's always a good way to practice math, is to make sure you can do it by yourself without looking at your notes and without watching the video. At some point you have to be able to do the whole problem by yourself, and then you can use the video to check yourself.